Hi students, so welcome back. We are continuing current electricity. In current electricity, today's topic, one session will be like a carbon resistor and its color coding. It is there in syllabus, and we have those questions. We used to get those questions or questions from that area in our board exam. And in Neet and JEE it may not be asked directly, but as a part of question that can be asked. Anyway, the knowledge on that, clarity on that is very much essential, so we will study that. Okay, so again this is a small part of resistance. So commercially we make resistance. Okay, many types are there. Okay, commercially when we manufacture resistance, first one type of resistance are by using alloys. This will be like a nichrome, constantan, like these kind of alloys will be used and resistors will be made. So now the advantage of this is we have studied about effect of temperature and resistance. Okay, when we increase or decrease the temperature, resistance will be either increased or decreased. In case of conductor, when we increase the temperature, resistance will increase. In case of semiconductor, when we increase the temperature, resistance will decrease. We have seen this in the last session. So in this case, what happens, this resistivity, the dependency is less. Dependency on temperature is either less or it is almost zero, almost nil. Okay, dependency on temperature is almost nil. And what about resistivity? Resistivity doesn't change much. So small change will be there, but it is not going to affect resistance much. So this advantage is there with this alloys. If we use alloys, the problem is limitation is there. Limitation is high value resistance is not possible. High value resistance is not possible with this kind of material if when we make with the alloys. Okay, so note it down. Nichrome, constantan, manganese is also there. Manganese. This is also example. Pause the screen and note it. Okay, so high value resistance is not possible. That is the limitation, practically speaking, when we go for commercial. Now second thing is using carbon. Okay, using carbon. So carbon resistors. Advantage is high value resistance can be made. High value resistance can be made. Then another advantage is if the value of resistance is too much, its size should actually increase. But here we can have compact and small small sized resistance is possible. Okay, we have these kind of advantages if we use carbon resistance. Okay, so here we can understand one thing, like since it is of small size, compact, small size, because of smaller size we cannot read the value of resistance. We cannot read the value of resistance. Say if we have written there 5 kilo ohm or 5 into 10 raised to 2 or something like that, or 50 kilo ohm or something like that, if we need to write, it is too small that we will not have space to write that. Okay, so to solve this, what we do, we will use color coding. Okay, color coding, all colored rings will be there, so that from that we will be able to understand the resistance values. So in carbon resistors, okay, in carbon resistors, color coding will be there, or colored rings. Okay, or we can say colored rings or color coding. This will be there to understanding resistance values. Okay, so we will now see like how this can be calculated. Say for example, if you have a resistance like this, we will have one band like this, or a color band or color ring, whatever. Okay, this will be one color, this will be another color, this will be another color, and there will be fourth band or fourth ring. So different colors will be there. Okay, suppose if I just give this black, this one like red, color, and if I give green, okay, so this is how it is going to be. So here it can be of no color or gold or silver. These colors will be there. So band 1 will be a number or magnitude we will take, just like 3 or 4 or 5, likewise we can take, okay, a number, magnitude, or any significant figure, we can say significant figure. Band 2 is also a number. Okay, band 2 is also a number. So what we will do, band 1 and 2 we will write here. So same number, significant figure. Band 3 is multiplier, just like a 10 raised to n. Whatever comes here, that will be as a multiplier. That also will be there. Okay, multiplier. So we can say order of magnitude. Okay, so by seeing these colors, we will be able to write like this, and we will be able to find the value of resistance. So band 4 is nothing but tolerance. Okay, tolerance, plus or minus so and so percentage. Likewise, what is tolerance? Say after making the resistance, when we using this color coding, we will be able to find the resistance value. From that resistance value, there will be something more or less, some value will be there. With that, something will be more, maybe 5% will be either will be more with that, or 5% of reduction will be there. Okay, so it can be plus 5% or it can be minus 5%. Say for example 100 we have measured. If the last value is gold, if it is gold, then it may be 105 or 95. Say for example, if the measured resistance is 100, then tolerance is gold, then plus or minus 5% when I say, so the real resistance value will be either 95 or 105. So 5% will be, we can be added or can be subtracted from that. This is how we can take. So this is nothing but variation in percentage from the given value. So we can write like this is variation. Okay, variation from the calculated value. Note it down. So how we will write that, how that color numbers we will write color. Okay, color. Next we will write number, band 1 comma 2, band 1 comma 2. Third is multiplier, then last one tolerance. Okay, so multiplier is third band, so this is fourth band. So okay, first we will start with the black. Okay, black, brown, green, blue, violet, gray, white. 1 2 3 4. No, something is missing here. Red, orange, yellow, green, blue, violet, gray, white. So these are the colors, 9 colors, right from white to black. So the number associated with the black is 0, brown is like brown is 1, red is 2, orange is 3, yellow is 4, green is 5, blue is 6, violet is 7, gray is 8, and white is 9. So here this is going to be 10 raised to 0, 10 raised to 1, 10 square, 10 cube, 10 raised to 4, 10 raised to 5, 10 raised to 6, 10 raised to 7, 10 raised to 8, 10 raised to 9. This is how. Each color represents first and second band can be replaced with these numbers. From the first and second band we will get the interpretation of these numbers. Third band we will have to write like this. Tolerance. If the fourth band is gold, then it indicates plus or minus 5%. Silver, this is going to be plus or minus 10%. If no color, then this is going to be plus or minus 20%. Okay, this is how it is. Okay, so there is a method, there is a code for remembering these colors. Okay, when I was studying in school, I also got the same thing. Nowadays also same code we are using for remembering this. So this is nothing but BB Roy, BB Roy, first letters of this BB Roy of Great Britain has very good wife. First letter, just take the first letter of each one and remember like that. Okay, I will write. B Roy of Great Britain has very good wife. So just the first letter of each color of this resistance can be taken here. BB Roy, black, brown, red, orange, yellow. Of this we have written in small letter. Great Britain, small letter, very good wife. So black, brown, so black, brown. So here B, three B's are there, so we should not get confused. This is nothing but blue. Then great anyway has got GR, so you can remember like this is green, and here this is going to be gray. Okay, remaining all the things will not cause any confusion. Black, brown, red, orange, yellow, no confusion will be created here. Okay, and violet, white. So wherever duplications are there, same letters are there where I have mentioned. Okay, so just remember these things where should not make mistake here. Black, brown, so this is going to be red, orange, yellow. Okay, Great Britain, blue, green, blue. Okay, violet, and this is white. Okay, so remember this code. BB Roy of Great Britain has a very good wife, and solve if you get any question. Okay, so we will do some simple problems here. Suppose if you get a resistance with some chords, like this is first band is yellow, second band is there, that is red. Okay, third band is there, which is nothing but brown. Fourth band is there, which is gold. So what is the resistance values? Okay, so B is 0, then B is 1, red, orange, yellow. So here B is there, this is 0, 1, 2, 3, 4. So 4 can be written for first one, number, magnitude. Red is 2. This is third band, brown is third band. So this must be written like a 10 raised to black, brown. So 10 raised to 1. So 42 into 10 raised to 1 ohm. Gold is there at the end. So plus or minus 5%. So this is the resistance value. So this is violet, blue, green, silver. What will be the resistance value? Violet, blue, green, silver. So B.B. Roy of Great Britain has very good wife. So 5, 6, 7, 8, 9. So violet is what? 7. Violet is 7. Blue is 6. Then green into 10 raised to green is 5. 10 raised to 5 ohm, plus or minus. Silver means plus or minus 10%. So this is the resistance value. One more question. Okay, so 3 bands are there. Fourth one is actually without any color. So this is brown. First one is brown. Second one is green. And this is blue. And brown, orange. Last one is grey. Okay, and fourth band is without any color. Okay, so what will be the resistance? So here resistance is equal to 1, brown is for 1, orange 3 into 10 raised to grey means what? 8. 10 raised to 8 plus or minus 20%. If there is no color, then plus or minus 20%. So this is how we can understand, we can find the resistance of a resistor, carbon resistor. Okay. Hi students, today we will see Ohm's law. Like already we have seen how Ohm's law has come from the charge carrier point of view, like using drift velocity, the relation between drift velocity and current already we have derived. So today I will show Ohm's law in vector as well as in scalar form. Okay, say Ohm's law. Okay, it is like at constant pressure, temperature and humidity, at a constant pressure, temperature and humidity, at a constant pressure, temperature and humidity, potential difference is directly proportional to current. And we can say like V is directly proportional to current, and V is equal to R into I, where R is a constant. Resistance only. Okay, resistance is a constant. So V by I is equal to a constant, and which is nothing but resistance R. So in Ohm's law the resistance must be constant. Okay, so that this is the condition for Ohm's law. At a constant pressure, temperature and humidity, Okay, note it down. Okay, so at a constant pressure, temperature and humidity, the potential difference is directly proportional to the current, or we can say potential difference across a conductor. Potential difference across a conductor is directly proportional to the current flowing through the conductor. Okay, so potential difference I add across a conductor is directly proportional to the current flowing through the conductor. Obvious, even if you don't write, this is well understood, but just I added for better clarity. Say for example, see, current at a constant resistance. So here resistance is constant. The physical conditions like temperature, preferably temperature, pressure, humidity, if they are constant, then we say current is voltage potential difference across a conductor is directly proportional to the current flowing through the conductor. So here we are writing V by I is equal to a constant, that is nothing but resistance. So resistance is always constant, or what? Can we say resistance is always constant? Whenever resistance is constant, we call them ohmic conductor. Only those constant resistance, those conductors will obey Ohm's law. There are non-ohmic conductors. There are resistances when voltage changes, resistance value itself will change. There are resistances like that. Okay, so 95% of our syllabus, 95% of our syllabus is all we deal with the ohmic conductors. We deal ohmic conductors. Okay, 95% of the syllabus, right? So this is what is Ohm's law. Now we will see V is equal to IR, okay, or V is equal to RI. V is equal to RI. This is what is scalar form of Ohm's law. Scalar form of Ohm's law. So here V and I are directly proportional when we write. This is potential difference V and this is I. The graph will be like this, straight line. So this will have a constant slope. So constant slope will be there. So slope is nothing but tan theta. Slope is equal to tan theta is equal to delta V by delta I. So this is nothing but resistance. So slope of VI curve, in which when it obeys Ohm's law, will be a straight line and its slope will be nothing but resistance. Now we will see vector form of Ohm's law also. Already we have seen that, but I have never mentioned there this is vector form, because we have not yet started just the full swing. We haven't entered into Ohm's law in full swing. So today only we have just started Ohm's law. So hereafter the equivalent resistances will come, then circuit theory will come from now onwards. So here we will see the vector form of Ohm's law also. Okay, so we know I is equal to Vena, you remember, drift velocity, charge of electron, number density, area of cross section. So here I is equal to, just I am writing like a NEA EE divided by m into tau. This is mass of the electron, this is average relaxation time. So all these things we have derived, we have got clear clarity. If you have revised it, then it is very clear, no confusion. Okay, then I is equal to what we do, NEA E into V by L M tau. We can take like this. So V is equal to M L by N E square tau into A. Correct or what? V is equal to M into L by N E square tau into A. N E square tau into A. So here, what about I? Yes, I is also there here. Okay, I is there. So here, this entire thing is nothing but resistance. This R is equal to ML by NE square tau into A. Correct or what? This is resistance. We have seen this. Now what we will do, we will bring this back like a V by L, and we will put like a M by N E square tau into I by A. Okay, now V by L is nothing but E, and this is nothing but rho. I by A is nothing but J. Electric field is a vector, current density is a vector. So this is the this is a vector form of Ohm's law. Okay. E is equal to resistivity into current density. So here we can write in another form also. So if we put J is equal to 1 by rho into electric field. So 1 by rho is nothing but conductivity. So J is equal to sigma E. So this is also vector form of Ohm's law. So resistance, those resistances which obey Ohm's law, okay, they are called ohmic conductors. We saw the graph like this. Okay, this is the graph. Okay, VI. Suppose there are non-ohmic conductors. Non-ohmic conductors, it will be like their graphs will be like this. So to some part it will be obeying Ohm's law, but remaining part it will deviate from Ohm's law, that don't obey Ohm's law. See, if you diode, this diode we will study in semiconductor electronics. This will come end of the +2. Okay, so here for some time there will not be any current. This is V, this is I. For some time there will not be any current. After some time there will be current. Okay, this is how. So this does not obey Ohm's law. This graph and these two graphs are different. Okay students, so we just completed the basic theory, the basic physics inside current electricity, like how current is generated, how Ohm's law comes from this charge carrier concentration, from all this drift to velocity, the relation between drift to velocity and current, what is current density. All these are a little bit dry, but we should have knowledge on that. Okay, once if we understand, then these things are easy. So from next class onwards we will get into the circuits. So circuit basics we will start from the basics of resistors. Okay, fine. So whatever we have learned till now, revise it, do extra problems, make it ready, make clear understanding on the subject. Okay, okay students, bye bye, goodbye.